All right, let's dive into the mind of an 18th century mathematical powerhouse, Adrien Marie Legendre. We're going to uncover this incredible blueprint he designed for finding perfect order inside of absolute chaos.
I mean, think about it. It's a huge question, right? Whether you're staring at a messy spreadsheet, facing a million different choices, or even thinking about the universe itself, how do we pull out a single, solid answer when the possibilities are literally endless? Well, this is where Legendre comes in. He had a system. He didn't see infinity as some scary barrier he had to stop at. No, for him, it was like a quarry, a giant, boundless source of raw material that he could carve beautiful, finished structures out of. So let's check out his toolkit.
To really get what he was doing, we're going to use a really simple three-part framework. You can think of it as Legendre's personal toolkit for taming the infinite, and it's all built on three ideas: psi, phi, and data.
So first up is psi. This is the starting point, the raw, infinite problem, the total untamed chaos of it all. Just picture an endless sea of numbers, functions, or data points with absolutely no pattern in sight. That's your psi.
Next, we bring in phi. And this is where the magic happens. Phi is the moment you impose a rule, a constraint, a guiding principle of symmetry. It's the chisel you use to start carving away at the chaos. You introduce one condition that forces everything to start taking shape. And all that work gets you to theta, closure. This is the beautiful final product. Once you've applied that rule of phi, you're left with something stable, something self-contained, a finite, elegant result. A golden set, if you will. You've successfully pulled one perfect answer out of infinity.
So you see the blueprint here, right? It's a process. First, you face the infinite chaos. Then, you impose a rule of symmetry. And finally, you achieve a closed, stable result. Now let's see how Legendre used this exact method to crack some of the biggest math problems of his day. First up, we're going to look at his work in mathematical analysis. This is where he took on a truly infinite mess and, using this toolkit, carved it into a set of perfectly ordered gems. Just try to imagine the world of all possible polynomial functions. It's an endless, tangled jungle. Legendre's goal was to wade into that jungle and find a small, perfect set of polynomials that could be used as a solid foundation, a basis, for building any other function you could want. And this is just a perfect example of his method in action. The infinite plenum, psi, was that entire jungle of polynomials. His symmetry rule, his phi, was to enforce this beautiful property called orthogonality. He basically demanded that on a specific symmetric interval, every polynomial in his special set had to be perfectly independent from all the others. And the result? Theta, a closed, complete, and stable basis of what we now call the Legendre polynomial.
He had done it. He'd carved a golden set right out of the infinite chaos. It's this beautiful, orderly system of functions that became fundamental building blocks for all kinds of problems, especially in physics. They pop up everywhere, describing things like gravitational and electromagnetic fields.
Okay, so he didn't stop there. Next challenge, elliptic integrals. Now these were a huge headache back then. They show up when you try to calculate the arc length of an ellipse, and the problem was there was just an infinite, uncountable variety of them. Every single one seemed like its own special, unsolvable case. So once again, psi was this untamed wilderness of integrals. What was his move? What was his rule of symmetry, his phi? He had this brilliant realization that every integral had a complementary partner. By grouping them up this way and boiling them all down to just three standard forms, he introduced this powerful symmetry, and that led to an absolutely incredible moment of closure, theta, a hidden, constant relationship that connected all of them. And this is the part that might just blow your mind. When he combined these integrals in just the right way, it didn't matter which ones he started with, the answer was always the same, pi divided by 2. Out of all that infinite complexity, this simple, beautiful, fundamental constant just appeared. That is the ultimate proof that you've sealed the context perfectly. You see the pattern here, right? And this wasn't just for abstract analysis. Legendre applied the exact same blueprint to the chaotic world of number theory, and even to messy real-world data. The way prime numbers behave can seem completely random. So Legendre took on a core question. If you have two prime numbers, let's say p and q, is there some hidden connection between their quadratic equations? You guessed it, it was another infinite, unpredictable landscape that he was determined to map. Now here, Legendre's phi, his rule of symmetry, was actually to invent a tool. He created this simple, elegant notation called the Legendre symbol. And just by creating a structured way to write down the problem, he tamed it. That new structure is what allowed him to finally see the closure. Theta, a deep, beautiful rule connecting any two primes, which we now know as the law of quadratic reciprocity. This law was so fundamental, so perfectly symmetrical that the legendary mathematician Carl Friedrich Gauss, who came after Legendre, improved it. He called it the Aureum theorem, the golden theorem. It's the perfect name for finding a golden rule in an infinite sea of numbers. Okay, for our last example, let's talk about something we all deal with today: messy data. Back then, astronomers had all these scattered, noisy observations of comet orbits. There were actually more data points than they needed, which meant there were an infinite number of possible paths you could try to draw through them. How in the world do you find the one true path? You know the drill by now. Psi was the infinite set of possible curves. Legendre's rule of symmetry, his phi, was just a stroke of pure genius. Find the one curve that makes the sum of the squares of the errors as small as possible. By squaring the errors, you treat the points above the line and below the line exactly the same way. It's a perfectly symmetric principle that carves out one, and only one, unique solution, theta, that perfectly balances every single data point. And what did that give us? The method of least squares. I mean, this is one of the absolute cornerstones of all of statistics and data science, used literally every single day to find the signal hidden inside the noise. A perfect way to bring closure to messy, real-world data. So when you step back and look at all of these different examples, you can see that Legendre wasn't just solving individual problems. He was using a universal blueprint over and over again. So this is the big takeaway, right? This powerful mental model. First, you identify the infinite chaos of the problem. That's your psi. Second, you find and impose simple, powerful rule of symmetry. That's your phi. Third, you use that rule to carve out a single, stable result, your theta. And the final check, like he did with pi over 2, is to look for those hidden constants that prove your new little world is perfectly sealed. This is so much more than a math history lesson. It's a real way of thinking. And it leaves us with a pretty fascinating question to chew on. From a business strategy to a creative project, what chaotic, messy infinity in your world is just sitting there, waiting for you to find and apply the right, elegant rule of symmetry?